Section 11.3, pressure and depth in a static fluid. All right, keyword here is static fluid. We will later see fluids that are moving with some velocity. That's when we'll need something known as Bernoulli's equation. But if it is static, we can use this approach. And this will help our understanding of the equations we get down the road. So to imagine static fluid, we could imagine having some pool of water like shown here. And within the pool, where all the water's just sitting there, no one's splashing around, we're going to imagine a chunk of water. So some chunk of water that's this rectangular cube-like shape, right? And we want to consider what are the forces acting on this chunk of water. Well, one of the forces that we still can't get away from is gravity, right? The force of gravity, the weight of it, is pulling down. So for however much mass this volume of water has, based on the density, we can figure that out, right? It has a certain amount of weight. Cool, that's pretty familiar. The newer forces that we have are forces that come from pressure, right? We're going to just focus on the vertical direction here, because all the side directions will be the same. The forces will just cancel. But on the top and the bottom faces of this block, right, there's pressure. So we could say there's some pressure 1 on the top part and pressure 2 on the bottom. And we know that the force experienced by that pressure is going to be perpendicular to the surface. So since we have a rectangular shape, the pressure below is going to create an upward force, and the pressure above is going to create a downward force. And that's what's shown in this effective free body diagram, right? Where we've added in, you could call this force 1, that's going down and pushing down on the top of it, and then force 2 down here is equal to whatever pressure 2 is, the pressure at point 2, times the area, where the area is going to be the area of this shape, right, of the flat face that this pressure is on. And we have the same area on the top and the bottom because we have this rectangular shape, which is convenient. Right, so what we're going to do is we want to see if we can create a relationship between points 1 and 2. So to do that, we're going to go back to the one and only, our favorite, Newton's second law, right? We've drawn our forces, so then we can say, okay, the sum of the forces in the y direction is going to be equal to the mass times acceleration. But since there's no acceleration in this case, because it's all static, not moving, the sum of the forces comes out to 0. Great, so now we just need to fill in these forces themselves, right? So notice we have F1 is going down in the negative direction. We also have mg, the weight, and that is going in the negative direction. And then force 2 is the only one going in the positive y direction. And so those need to all come out to 0. We're going to do a few more steps in the derivation here, but this is the key starting point, how we can connect Newton's second law to this derivation. So here it's written a little more nicely. The sum of the forces in the y direction is equal to 0. Now what we can fill in is that the force is just equal to P1 times A or P2 times A for each of those forces. So force 2 is going to be P2 times A, force 1 is P1 times A, and then mg. We're going to put the negative forces, the ones that are down, we're going to add them to the other side. So if I add P1A to both sides and add mg to both sides, that'll cancel it out from the left and we'll add it to the right. So that we get pressure at point 2 times that area is equal to pressure at point 1 times the area, which is equal to mass times gravity. And as I mentioned, with fluids, we often don't tend to work in terms of mass. It's weird to think like, oh yeah, I have a good mass of water here in my water bottle. I'm glad I can take that in. No, we tend to talk in terms of volume, right? That this is 750 milliliters. Cool. So we're going to convert that mass into volume times density, times the density of the material. So let's put a few more of those steps up here. All right, so we plug in the volume rho for the mass. So rho times volume is the mass. Another thing we can note is that the volume is just going to be the overall volume of this shape. So we know the area of the top and the bottom we've called A. We also have the height of this rectangle is h. Fill that dimension in too. That means if we want the total volume, we can just multiply the area of the top or bottom times h, and that will give us our volume of the rectangular cube. So we'll fill that in there, and the convenient part of writing the volume in terms of the area is now we notice that all three terms have that same area. They're all written in terms of the area of the top or the bottom. So that's something we can divide out. It's in all three terms, so it will cancel out. So when we divide by A on both sides, or really every single piece of this, what we're left with is this equation. Pressure 2, notice there's no more A, it's just pressure 2 is equal to pressure 1 plus rho hg. So the density of the fluid times the height times g, our acceleration due to gravity, 9.8. What does this mean? Well, this means that given some amount of height of the fluid, the pressure at point 2 below it is going to be larger than the pressure at point 1. It's a higher pressure as you go deeper. And this is something you've probably experienced if you've gone swimming or if you've gone scuba diving, especially if you have a deep pool, right? When you swim down into the deep end, you can feel the increase in pressure pushing on you. Why is that there? Why does the pressure change as you go deeper? Well, it has to do with the fact that the water below has to support the extra weight of all of the water above, that little mg. Doesn't seem like a lot, but as you add more and more water above, that's now all pushing down. So you have to have more pressure present to support the water above. So this is an equation that we can use anytime we have a static fluid, something that's not moving, where we'll often use h here as the depth. Or it's the distance between point 1 and 2. That went way off the screen. So we'll just bring it over here. So the distance between point 1 and 2 is our h variable. Right, and P2 note is always going to be deeper. So that's something to keep in mind here. Now that we've started to see these concepts, let's see it in some examples and see what we can see from that. So first, a conceptual example with the Hoover Dam. Lake Mead is the largest wholly artificial reservoir in the United States. The water in the reservoir backs up behind the dam for a considerable distance, 120 miles. That's more than shows up in this picture, right? So it keeps going for 120 miles. Whew. Suppose all the water in Lake Mead were removed except a relatively narrow vertical column, right? So, okay, we put a bunch of land in so we don't go 120 miles back. We just have this vertical column that's super narrow. Would the Hoover Dam still be needed to contain this amount of water, or could a much less massive structure do the job? I'd like you to reflect on this, so go ahead and pause the video so you can think about it. All right. So the key here is that the water at the top isn't that hard to contain. But as you go deeper, it's going to be a higher and higher pressure, right? So the pressure down here, which we could call, say, pressure 2, compared to the pressure up at the surface, pressure 1, is much, much greater. And that just depends on the height. It doesn't have anything, or the depth is another way of putting it. It doesn't have anything to do with how much there is horizontally. If we have a huge amount of pressure here, that means the water down at the bottom is going to be exerting a huge amount of force in all directions. But the one that we care about is the direction of the Hoover Dam, because that's the direction we're trying to keep it in place, right? The land does a great job of holding the water in place. But there's this huge amount of force there. So if we have the same vertical column of water, we're going to need just as much Hoover Dam to hold that in place, even if it's way less water, just by virtue of having it be so tall is the key. Let's look at another example, example 4 with a swimming hole. Points A and B are located at a distance of 5.5 meters beneath the surface of the water. Find the pressure at each of these 2 locations. All right, so we notice they gave us a nice picture. 5.5 meters below the water is point A, and then there's a rock in the middle, and so sort of over here off to the side is point B. So what do we know here? Well, first off, what are we looking for? We're looking for the pressure at each of these locations. So that means we want to find the pressure at point A, and we want to find the pressure at point B. So that's worth identifying just to start. It also doesn't mention the fluid is moving, so we can assume it's stationary, that it's a nice, still swimming hole. So that means we can use that static equilibrium equation that we just derived that relates the pressure at point 2 to be equal to the pressure at point 1 plus the density times the height times gravity. All right, so looking at this, we notice that we have a distance of 5.5 meters beneath the surface of the water. This could be our height, our h. If so, then that automatically tells us what P1 and P2, or where those have to be, right? Because this h is going to be relative to P1 must be at the top of that, and P2 is at the bottom of that height, or that depth. So P2, notice, is right at point A, so that's great. We can find the pressure at point A with this equation, solving for P2. So that equals PA. And we know our height, we know G. What about the density here? Rho. Well, that's where we can go, oh wait, it says it's a swimming hole. And if it doesn't specify otherwise, you can assume the swimming hole is just standard water, right? So then we can look at that table that we have and go, oh, water. We know the density of water. It's that 1,000 kilograms per meter cubed. Great. So now we know that as well. This means we're in good shape, except, oh, what about P1? Do we know anything about the pressure at the surface of the swimming hole? That's where we notice, okay, at the surface of the swimming hole, that's where you and I are. That's at sea level. So there we can assume it's just going to be our atmospheric pressure. So if you're just in open air, it doesn't mention being any crazy height differences or anything else going on, you can always assume 1 atmosphere of pressure. That's our standard default, but you do have to be careful because, as I mentioned, 1 atmosphere is not yet in our pascals of SI units. So in pascals, we'd have to write this as 1.013 times 10 to the 5th. PA. Right. So now we're in good shape to solve, and we can get the pressure at point A. What about the pressure at point B? How will that compare? Well, if we look at our equation, it has the pressure at point 1 at the surface, okay, plus rho times h times g. It just mentions the depth. It doesn't mention anything about horizontal dimensions. So the fact that point B is at the same depth as point A tells us the pressure at point B is also going to have to be equal to the pressure at point A. Pressure B is equal to pressure A. That the horizontal direction doesn't matter, just how far down you go. Now, it would make a difference if you try and swim up and there's no surface above you, right? You'd run into the rocks. So it's not that they're at the same point, but in terms of pressure, the pressure is the same. All right, so now we can plug and chug. So we plug in our atmospheric pressure, 1.01 times 10 to the 5th pascals, plus the density of water times G times H, our depth. And note this is often a way the equation is turned around, where instead of being rho times H times G, it's written as rho GH. So density times gravity times depth. And so if you calculate that out, you should get 1.55 times 10 to the 5th pascals. And that is equal to pressure A, and that's also equal to pressure B. Note we would have gotten a very different answer if we had plugged in 1 ATM here. Right, we would have gotten just the 0.54 times 10 to the 5th pascals. So it's really good we included this extra 1.01 times 10 to the 5th pascals. That made a big difference in our answer. All right, so this introduces the idea of pressure and depth in a static fluid.